A 90-year-old cosmological cold case may finally have been solved. For decades, there was a silent operator lurking in the shadows of the universe, one that doesn't emit light or reflect it, one that our telescopes can't see, despite the fact that there is 6 times more of it than there is of the regular matter that makes up you and me. What I'm talking about, of course, is dark matter. It's fundamental to our models of the universe, and yet we still don't have a clue what it is. Physicists across the globe are using state-of-the-art particle accelerators, underground laboratories and telescopes in an attempt to detect direct evidence of this elusive matter, with 0 success. But in November 2025, a paper was published that rocked the scientific community. Whilst trawling old data from the Fermi telescope, a researcher may have finally captured a glimpse, a telltale signature coming from inside the Milky Way. But how can we be sure it's dark matter producing this signal? And will this mystery finally help us explain what dark matter is after all this time? I'm Alex McColgan, and you're watching Astrum. Join me today as we probe this juicy new lead and answer the question that I know you're all thinking: did we just see dark matter? This is Fritz Zwicky, a Swiss astronomer born in 1898, who spent most of his life working at the California Institute of Technology in the United States of America. His time at Caltech began as part of a research group studying the physics of crystal structure, but he was soon swept up in the exciting, newly emerging field of cosmology. Probing the mysteries of the cosmos became Zwicky's passion, and while he was well known for having an eccentric personality, his biggest legacies were his discoveries. His research into the origin of cosmic rays led to his conceptualization and coining of the term supernova. He catalogued tens of thousands of galaxies, and over the span of his career, published hundreds of papers on a wide array of astronomical subjects. But despite all this, he is best known as the father of dark matter. In 1933, aged 35, Zwicky was measuring the redshift of galaxies using the Mount Wilson telescope, the very same that Edwin Hubble had used to prove our universe was expanding just a few years before. Redshift is a phenomenon whereby the light from a distant object is stretched on its journey from source to observer. The more it's stretched, the longer the wavelength becomes and the redder the light appears. This indicates that the source is moving away. Zeroing in on a small patch of sky in the Coma Berenices constellation near the Milky Way's North Pole, Zwicky spotted something incredible. Galaxies within the Coma cluster were traveling at speeds that seemed impossible given the commonly accepted laws of physics. Sitting at his desk, he began to calculate the difference in velocities between 8 of the galaxies. It was more than 2,000 kilometers per second. These galaxies were traveling at such high speeds that this cluster should have ripped itself limb from limb long ago. How could what he was seeing with his very eyes be reconciled with the figures on the page? Calculating the mass of the cluster, Zwicky realized that the gravitational pull of the stars and gas alone was not strong enough to stop the galaxies from escaping one another. In fact, he worked out that the system needed around 10 times more mass than had been observed just to stay together. He concluded that something more must be at work, something dark, enough to be concealed from view, lurking deep within the cluster to anchor these galaxies in orbit. What was this dark matter? The question of dark matter's true identity has continued to plague cosmologists since Zwicky's study on the Coma cluster over 90 years ago. Dark matter was so called because of its very nature. This is a substance that doesn't interact with light. This is a problem because light is the primary tool we use to probe our universe and understand how it works, from the micro to the macro. Dark matter doesn't emit light, nor reflect it, and it doesn't even absorb light to cast a shadow. So it is truly invisible. And like Zwicky, we instead have to observe its ghostly effect on objects that are visible to us in order to perceive its presence. We know dark matter is there, and that it exerts a gravitational force on visible matter, but we don't actually know what dark matter is. The two leading theories today are WIMPs and axions, though we've not yet found hard evidence for either of them, until November 2025 that is, when that news erupted from the University of Tokyo. Astrophysicist Dr. Tomonori Totani had found a signal never identified before, emanating from the Milky Way, and it appeared to have the properties of being produced by WIMPs. Was this the first observational evidence of dark matter? To answer this question, we need to understand the nature of a WIMP. No, we don't think they are particularly shy or cowardly creatures, but they have been highly successful in evading our detection so far. This is a class of particles predicted to exist within an extension of the standard model of particle physics known as supersymmetry. WIMPs, being weakly interacting, neither absorb nor emit light, and they very rarely interact with other particles other than through gravitational attraction, which ticks many of the boxes we're looking for when it comes to searching for dark matter. These properties also make them very challenging to observe. However, there is a way in which we should be able to detect the presence of WIMPs, and this is through a process called annihilation. In the standard model, all particles have an antiparticle pair. For example, the proton has its antimatter counterpart, an antiproton. Both the proton and antiproton have the same mass, but possess an equal and opposing electric charge. Another example is the negatively charged electron, whose pair is the positively charged positron. You might not realize it, but antimatter is everywhere. It's even emitted by your regular banana. When a particle meets its antiparticle, they cancel each other out and annihilate, releasing a signature burst of radiation, often in the form of photons and gamma rays. The energy profile of those gamma rays can be measured, and is related to the mass of the original particles. We believe the mass of a WIMP to be between 10 and thousands of times that of a proton. Yes, that's quite the range, and the resulting gamma rays would have a corresponding energy signature. If another eccentric physicist by the name of Albert Einstein is coming to mind for you right now, you'd be correct to make this connection. Einstein's famous equation E=mc² revealed that mass and energy are interchangeable, and the annihilation of a pair of particles is the most beautiful and fundamental example of this formula in action. Anyway, back to dark matter. Gamma rays are incredibly helpful clues for astronomers. Like fingerprints left at a crime scene, they indicate where activity has occurred in a region of the galaxy, and where it may be pertinent to take a closer look. However, both gamma rays and fingerprints can be left by a myriad of different sources, which creates a serious issue. Gamma rays are created and released in all sorts of astrophysical processes, from the hot accretion disks around black holes to the death throes of a dying star. So how can we detect the true signal of dark matter, if it is the annihilation of WIMPs, in such a maelstrom? Well, it takes a new and honestly quite painstaking approach. In early 2024, Dr. Totani began dredging through the Fermi telescope's enormous back catalogue for clues in solving this dark matter conundrum. The Fermi telescope is an incredible piece of hardware designed to spot gamma ray bursts in distant galaxies. And while I don't think you'll be able to spot dark matter, you can see some of those spectacular galaxies it is holding together for yourself with the Dwarf Mini Telescope. This tiny powerhouse of a telescope is so easy to use. Just pop it on a tripod, connect it to your phone, and choose what you want to see. The Dwarf Mini auto-tracks your target and takes multiple photos, which it stacks to produce breathtaking results. Right now, it's galaxy season for skywatchers in the Northern Hemisphere, and I managed to capture this stunning image of the grand design spiral galaxy, Bode's Galaxy, or M81, on a clear night last week. You can also see the Cigar Galaxy, M82, right next to it. That's 2 for 1. You can't make out these structures with the naked eye, so watching them magically appear on my phone screen using Dwarf's built-in stacking software was a real treat. Within moments, I had an image ready to share straight to social media with just one click. And if you want to take photos like this with minimum effort, I can't recommend this little telescope enough. Just scan our QR code or follow the link in the description below to see for yourself. Astronomy enthusiasts who use the code Astrum5 at checkout get 5% off their purchase. Now, just like Bode's Galaxy, our own Milky Way is a spiral, flat and wide. The gravitational geography of our galaxy dictates that the majority of visible matter is concentrated in the galactic plane. From the outer tendrils of the spiral arms to the densely packed galactic center, all manner of stars, planets, and our behemoth supermassive black hole, Sagittarius A star, make up our home galaxy. Naturally, this means that the majority of sources of high energy radiation, that is, gamma rays, are located in the plane too. But when we observe the movement of stars and gas around the galaxy, this indicates that the dark matter has a different shape. It is not concentrated in the galactic plane as we might expect, but it extends around the Milky Way in a sphere structure termed the halo. By scraping 15 years worth of Fermi data and blocking out the blinding gamma-ray rich center of the galaxy from his study, Dr. Totani has been able to diligently remove known astrophysical producers of gamma rays from the background, source by source. What was left has floored the scientific community and me. Honestly, this is so exciting. A unique pattern of gamma rays in the ghostly shape of the Milky Way's predicted dark matter halo. But Dr. Totani's research takes this theory another step further. Not only were these gamma rays revealed to be populating the correct shape and structure to be the dark matter halo, but they had an energy spectrum peaking at 20 giga-electron volts. This is in the suitable range to be caused by WIMP annihilation. If this gamma ray signal is from WIMPs, it cannot be underestimated. This observation will have changed the face of physics forever. But before we can be absolutely sure, there are still a few puzzling parts of this case to solve. Firstly, we're still getting to grips with exactly how much mass WIMPs do have, and therefore the energy signature expected to be produced during annihilation. After all, they are still only theoretical particles. And while teams at particle accelerators around the world continue to have success in constraining their properties, we're so far limited in working with the rather wide range I mentioned earlier. There are also concerns over the population density of WIMPs required to produce an annihilation signal as strong as the one measured in Dr. Totani's study. WIMPs are relics created from particles present at the Big Bang, and by studying the early universe through evidence like the cosmic microwave background, we have a good sense of the numbers of each particle we expect to be populating the universe today. The signal seems like a much denser collection of WIMPs than we would expect to be possible from this evidence and particle physics models thus far. But this field of research is one that can't afford to ignore new leads. And right now, WIMP annihilation, and therefore dark matter, is a strong contender for what this gamma ray signal might be. Some even argue the strongest. But given we've never seen a WIMP, many are erring on the side of caution. Professor Carlos Frank, a lifetime researcher of dark matter and one of the originators of the leading cold dark matter theory, including WIMPs, has likened finding the source of dark matter in significance to humanity as Charles Darwin's theory of evolution. It's not something you claim to have found unless you really are sure. So scientists are excitedly working to help better determine the factors that could be at play in Totani's signal so that they can untangle the snags and gain a more definitive answer. One thing is for sure though, the more we discover at the Rubicon of this fantastical micro-world of quantum and particle physics, and the vast expanse of cosmology and general relativity, the closer we get to solving the biggest mystery of our universe in unifying the two. So, is this enough to lay this cold case to rest? Unfortunately, not yet. While this is brilliant new evidence, and a well-needed re-injection of energy in what has been a relatively stale search for dark matter of late, there is still more work to do before we can close the case file on WIMPs. If WIMPs really are at work here, we would expect to see similar gamma ray signals in our dwarf galaxy neighbors and beyond. So, what can we do next? The latest investigator on the scene is the new Vera Rubin Observatory in Chile. Vera Rubin was a prolific researcher in the field of dark matter. In the 1970s, she discovered the effect of dark matter on the velocities of individual star populations in over 60 galaxies, and it was Vera's work on categorizing these effects that brought serious consideration to the theory for the first time. This was a pivotal moment in convincing the scientific community that dark matter was real and a valuable thing to study. The observatory of her namesake came online in June 2025, and datasets from the first schedule of observing are expected for release in 2026. Through taking hundreds of images of the southern hemisphere sky each night, amounting to 20 terabytes of data, or the equivalent of 78 standard iPhone 17s, the Rubin Observatory hopes to uncover objects never before seen in our night sky. At the end of the first 10-year survey, this raw image data is expected to sum up to more than 60 petabytes, or 60 million gigabytes, in a monster effort to reveal the secrets of our universe. Dark matter makes up more than 80% of all the matter we know, and it is fundamental to the very fabric of our existence. Its gravitational influence enabled the formation of the first baby stars and galaxies at the cosmic dawn. It sculpted our cosmos to look the way it does today, and dark matter will continue to influence the fate of our future too. This new study, presenting the first indications of the presence of WIMPs in our galaxy, is the most exciting development in the observational search for dark matter for decades. I can't wait to see the fresh research that stems from it. In Switzerland and South Dakota, from Chile to low Earth orbit, brilliant human minds are on the case to find the true nature of dark matter, elusive WIMPs or not. So stay tuned, because we might just be on the cusp of a dark revolution, and isn't it a thrill to watch it unfold? There's a reason these educational mini documentaries are free for everyone. It's not just the ads or sponsors, but it's thanks to our hundreds of Patreon members who make it possible for everyone to get the best possible content. They are the foundation that keeps Astrum steady and focused on quality over clicks. Every video you watch exists because there's a community behind it that values learning and curiosity. If you'd like to be part of that group, the people who keep space education open to everyone, join us on Patreon through the link below. We would love to have you.